Welcome back my dear friends and students. A very good morning, good afternoon and good evening to all of you, and welcome to this DADM 1, which is Data Analysis and Decision Making 1 course under the NPTEL series. And as you know, this is a course for total duration of 12 weeks and we are in the last week, and the total duration for the course is 30 hours, which is 60 lectures. And each week, as you know, there are 5 lectures, each being of for half an hour, and I am Raghunandan Sengupta from the IME department, IIT Kanpur. So, we have 4 classes left or 4 lectures left for this DADM 1, and as we know that we are considering canonical correlation method. To just to recap, even though I am sure the methodology how we went about is clear. So, we consider a set of x random variables, and we want to basically find out the relationship actually which is existing between x's using so called proxies, or which give the best relationship from the x using y set of random variables. And we find out, as you know, that one set of vectors A and vectors B, such that in reality what we try to do is that we try to find out a linear combination of a row vector A with x and B with y, and find out the relationship of A1 x, A2 x, A1, A2 I am mentioning they are vectors, such that the overall variance is reduced step by step, but we try to get the maximum variability in each of the linear combinations, such that we are able to give the maximum information or the relationship between the x and y set of random variables. Now, we also remember that in the optimization case, we will try to maximize the covariances, linear combination of the covariances of x and y, considering A and B being multiplied. A and B, as I said, they are some constants to be found out, and based on that we try to give the relationships. Now, once we do that, we would basically find out the correlation coefficients, the best correlation coefficients, which is rho star square, and each of the correlation coefficients which we found out, if you remember in the last class I discussed that the correlation coefficients would be in the decreasing order. That means, the first set would take out the maximum information, second set would take out the second set of maximum information, so on and so forth for the third, fourth, whatever number of sets we want to, but remembering that they would be orthogonal to each other. So, if you remember, we found out in the last class the covariances, and between the x and y's, which are basically equal to the u and v, because u and v are the linear combinations of x and y, u being linear combination of a and x, and y being the linear combination of b and y, v being the linear combinations of b and y. So, we are going to find out the correlation coefficients of the covariances between u and x. So, if you remember, so we had to find out a x. So, these are vectors, remember, vectors are matrices. So, I am not able to draw the bold, but remember they are in bold when you write them. Similarly, we want to find out b and y. Let me use the other color, b and y. So, the first case would be the covariances happening between a and x. So, this is what we need to do. So, the covariances of u and x would actually be the covariances of u is a combination of a into x. So, obviously, it would be the covariance is being multiplied by a, covariance being for x and x. So, once we find it out, so this is the covariances which is existing between u and x. U is the linear combination of x. So, they come out to be as given. So, it can be found out, you just multiply them and find out the covariances between them. So, we already have, remember, so this would technically be, So, there are 3 x's if you remember for the last example, n cross 3, n being the sample size which was 600. So, the first one will be, I will use this the subscripts x 11, x 12 and so on and so forth. So, the first one will be sigma x 11 and the last one will be x 33 and the second element will be sigma x 2 and of the diagonal element which is this one are mirror image, this one is mirror image and this one would be the mirror image. So, those values when you multiply with A is a vector. So, the values come out to be minus 0.62, I am just 61, I am just reading the first 2 decimal places. The second element is along the row is minus 0.07, minus 0.20, then the third rows are plus 0.26, plus 0.230, minus 0.21 and the third row being minus 0.06, plus 0.64, plus 0.19. Similarly, we need to find out of the covariances between V and Y, which will be the covariances which we find out considering B and Y. This is how we will do it. So, again if you remember, we have this is y 11, y 11. Now, remember the size of sigma x x and sigma y y are different. In x you had 3 variables x 1, x 2, x 3 and y you had 4 variables y 1, y 2, y 3, y 4 depending on the level of dependent structure we find out. So, this will be sigma y 2, sigma y 3, sigma y 4, So, I should basically expand and of the diagonal element would all be mirror images. So, these values which you write would be sigma 11, y 1, y 2. So, this will be mimicked here. Similarly, you can find out all the variables. The values come out to be as given here, the first row being. So, remember just see, watch the size, it is 4 by 4 because you had again I am repeating, please do not mind, the y had 4 random variables, x had 3 random variables. So, x was 3 by 3, y was 4 by 4, the values being minus 8.8. I am going to read only the first decimal places minus 8.8, minus 8.8, minus 7.5, minus 6.7 and so on and so forth for the second row and the third row. Now, remember one thing, the values which we found out are actually the values based on which we are trying to minimize maximize the variances of the optimization problem. Subject to the conditions, we remember we want to basically make A mu these values and use the such then conditions were as 1, this is related to the variance covariance matrix for x and this was related to y. Now, we will go to find out the correlation coefficients and the correlation coefficients obviously they are, remember we are trying to find out the orthogonality. So, obviously, the of the diagonal element would be 0 and the principal diagonal would be all the variances which we have. So, once we find out the actual vector of A multiplied by rho x x. So, the values are this is the standard deviation of x 1, similarly x 2 and similarly the last one, because there are 3 values. So, the corresponding values would be 0.67, 0.70, 0.34. So, obviously, the others as noted down are 0. You can find it out very easily by multiplying A with the corresponding variance covariance of x. Only remember the size, again I am repeating, p or for x it is 3, for y it is 4. Similarly, when we go to find out the correlation coefficient between v and y, which is here correlation coefficient between this should be v with y, the values would be again the principal diagonals are the standard deviations of y 1, standard deviation y 2 till the standard deviation of y 4, and of the diagonal elements you can find out. So, the values come out to be as given here. Now, we will go into a little bit different topic, which is structural equation modeling. So, I will go through the theoretical basis a little bit slowly. We will consider structural equation modeling, where it works somewhat like in the principles of multiple linear regression, and I will basically go slowly with the assumptions and then go through the theoretical build up of the standardized structural equation modeling. So, structural equation modeling is a methodology which is basically a sort of extension of the multiple linear regression, and it is quite heavily used in social sciences, where the relationship which is to be found out between the variables are considered, where the qualitative factors can also be considered in a different way. So, what are the general bullet points of structural equation modeling are as follows. It works with multiple related equations simultaneously. So, this simultaneous so called equations technically should be linear, but we will consider them to be non-linear as and when required. This allows for reciprocal relationship. Now, reciprocal relationship is, say for example, if x and y are related, that means x is related to y, and the relationship is, say for example, 0.23, then the reciprocal relationship, that means how y will be affecting x, need not be like the covariance variance matrix, which is standardized and along the principal diagonal, across the principal diagonal it is a mirror image. It would not be the case depending on the problem structure. So, it is able to model constructs and for the latent variables also. Latent variables need not be always in qualitative and quantitative in nature, they can be qualitative in nature depending on how the effect of the latent variables can be considered accordingly. So, it allows the modeler to explicitly capture unreliability of measurements in the model. So, unreliability of the measurements in the model, I will briefly go through it with a diagram. It is not a part of the structural equation modeling concept, but I will just consider that from a very simple point of view, how we consider reliability or say for example, stochasticity or non-deterministic nature in the data. So, this fourth point I will come to that using the concept of which is a simple diagram. These variables can be explanatory in one equation and similarly they can be response in other equation. So, if you consider in any very simple case, when you are considering a multiple linear regression, in multiple linear regression what you have y which is dependent linearly on x 1, x 2, x 3 plus a white noise. And we did consider that the x values which are there, x random variables which are there, they are independent of each other. That is why if you remember I did mention that when you are trying to find out the rank of the x matrix, it should be exactly equal to the number of rows or number of columns depending on number of independent variables which they are. That means, any of the rows or any of the columns cannot be expressed as a linear combination of the other rows and the other columns. We also considered in multiple linear regression the relationship between the random variables x's and y's and the errors epsilon should not be there. Then we will also we did consider the relationship between the errors from time to time is independent, and I will draw a diagram there also for the multiple linear regression. I did draw it, but I will still highlight it as required. So, the variables depending on their construct can be explanatory one set of equations, can be the dependent or independent variables depending on the modeling framework. So, we will have indirect effects on mediating variables which would be there and which will basically have an effect how they can have a relationship which where random variable x1 affects x2 and then again x2 affects x3 and again x3 may affect x1. So, this looping method can be considered. In structure modeling, it compares the performance of model across multiple populations. So, depending on the what samples you are taking from which sets, they will basically be compared in order to give us the best fit model. And identifiability of the parameters should be there, so that we are able to find out the set of parameters which really affects the so called simultaneous linear or nonlinear equations as the case may be. So, before I go into structure modeling, I will first go into the concept of reliability or stochasticity, and then from a very theoretical point of view give you an idea and then go into the structure regression modeling. So, I will try to make blank slides as I do and then I explain it accordingly. So, let me create some blank slides for our discussion. So, this is the general concept which I wanted to discuss about simple stochasticity, and we will consider a set of distributions initially to be normal and then slowly relax it. So, consider that we have I will just slowly and very simply state the let us consider the multiple linear regression first. So, you have y is equal to alpha plus beta 1 x 1 plus beta k x k plus epsilon. So, we have considered that x's and y's are all normal. Similarly, epsilon is also normal with a certain mean and a certain standard deviation, and for epsilon we considered the mean value was 0 and the variance was 1 or sigma square. Now, consider that on the other hand consider a simple optimization model also very simply. So, I am trying to basically find out the so called the errors and trying to minimize the errors. So, you have the errors as given, this is the actual value, this is the predicted or the forecasted value, I square them up and then I try to minimize. So, consider the problem is this is the objective function in general. So, I will basically consider a simple objective function with constraints. So, consider it is single objective, minimum maximum does not matter, only concentrate on how the constraints are developed. So, I will basically consider optimize some f of x which is a function is can also be epsilon square. So, f of x 1 x 2 for the time being consider that the random variable which we are going to consider in order to minimize or optimize consists of 2 random variables also, because it will be easier for me to draw, that is why, that is the only reason. So, in the higher dimension it can be done accordingly. Subject to constraints, again some g 1 x 1 x 2 is say for example greater than or equal to b 1. These are just constants, consider b 1 is a constant, and similarly consider g 2 x 1 x 2 being greater than or equal to b 2. So, this greater than sign less than sign can be tailored according to your problem, and there are other constraints. Now, let us draw the diagram how it can be done. So, let me draw a 2-dimensional one. If you remember, I mentioned that I am going to consider x 1 x 2 only, considering that it is easy for me to explain. Point 1. Point number 2, let us also consider x 1 and x 2 are only positive, that means need not be, but let us consider them to be positive. So, this function g1 x1 x2 and g2 x1 x2 are non-linear. So, they are greater than b1 b2. So, that can be handled. So, let me draw them to be non-linear. I am just arbitrarily drawing a diagram. So, it will make you understand. So, now consider this optimization model. Let me segregate it. So, my drawing is easier. So, let us go step by step. Consider the optimum solution for this optimize f x1 x2 given g1 and given g2 is in the deterministic case is at the boundary. Obviously, it will be at the boundary. So, once we the x1 and x2 for simplicity I am considering x1 along x axis, x2 along y axis. So, this deterministic point is say for example, A. But now, let us go one step forward. Consider the function, let me highlight it. So, with different colors. So, this is probabilistic and similarly, this is also probabilistic. So, how do we analyze that? So, the function first one g1 which is yellow in color, we will consider this is the point. So, now I am going to basically highlight the equation as yellow for the first function, equation 2 which is for the second function. Consider they are normal. So, if it is normal, the mean value of that constraint actually would be the lines which I have drawn. So, the mean value means the expected value. So, as you repeat try to find out different values of x1 and x2, it will be a random variable, but it will have an expected value. So, the expected value of that line or the constraint I am considering to be the line which is green and yellow in color as shown in the slide here. Now, there are some probabilities. So, the mean values means if there are probabilities, they would basically be shifting either onto the upper side or on the lower side depending on what is the overall randomness which you are trying to bring. Also consider the space which we have for x1 x2, this is the feasible region. So, I am just highlighting it. So, this is the feasible region and these are the infeasible region which is here. So, these are the infeasible region where the solution cannot take place. Now, how it happens? So, let me I will be switching the slides. So, please bear with me. So, generally the first equation, just notice on the first equation is g1 x1 x2 is greater than b1 and g2 x1 x2 is greater than b2. So, let me write using the probabilistic one. So, it will be probabilistic one means the first equation basically is probability of g1. I will only write g1. So, without mentioning x1 x2 which is you can understand is greater than equal to beta 1, but this is true for a value of say for example, alpha 1 as per the problem. So, alpha 1 is basically if you remember this level of significance which we had considered, it is something to do with this. So, this is equation 1. Similarly, the second one is probability of G2 greater than equal to B2 is greater than equal to alpha 2. Again alpha 2 is basically a level of significance which we have. So, now let us basically highlight these two through the diagrams. So, the first part is this is the mean value. So, the mean value is, if you remember this mean value which I have drawn. So, let me use a color for the first equation. This is actually the yellow line which I have drawn. So, similarly, I will draw the green one later also. So, the distribution is like this. So, there would be some alpha value, alpha 1, alpha 2 value. So, G 1 is greater than B 1 by value of alpha 1. So, this would basically be given as alpha 1 depending on the level of significance. So, this is for equation 1, this is equation 2. So, I will draw it here also. So, the mean values obviously would be different and the variance can also be different. So, how I am going to include that? Let us go. So, I draw the mean value was green in color. What was green in color? What I am drawing is this one, the mean value here. We will come to the red point which is A later on. So, it got a, so this is alpha 2. Remember the variances are different. Now, if there is a dispersion for both equation and equation 2, how do we basically consider them? So, let me, so at this internal part, the area which is marked in blue is the feasible region. So, I will just remove the blue color in now to draw it more clearly. So, this is how the lines would be. So, they are fluctuating. So, there would be a mean value over and below. So, the below part is infeasible. So, obviously, it will not be considered, and for this one again there is a above and below. Below part will not be considered because infeasible. Now, what you actually have is, I will use the red one, they would be a circle, because why circle you will consider, and the circle would be true if both the variances are true. So, I am going to draw the circle depending on the way the equation varies. So, this would be the loci of the midpoint. So, consider the circle. Why it is circle? Consider you are looking at a football from the top, you are taking slices. So, if you are taking slices, it means the dimension in one direction and orthogonal directions are of the same radius, which means the variability in both x 1 and x 2 directions are same. That means, the variability which you are going to consider for both equation 1 and equation 2 are the same. Now, consider that you have a rugby ball or the so called American football. So, if you place the American football either on a horizontal space or in the vertical space, in the sense you are placing in front of you, then the variability along the x 1 and x 2 direction would be different. So, in that case the variability which is there for equation 1 and equation 2, which is of the constraint 1 and constraint 2, would be different. So, we will draw that later on, and obviously, as the distribution change we will consider it later. Now, consider for the time being the variabilities are equal, and you are trying to draw the loci of this center of the variability in such a way that as alpha 1 and alpha 2 change, you are able to trace it out. So, with this I will just close this 37th lecture and continue the flow and trying to explain how we can consider the concept of stochasticity in the model, and then try to go into the structure equation modeling in detail. So, this slide for the first time I will keep this slide and use this slide also for the 30th lecture as required. So, I will end it here and have a nice day, and thank you very much.